So let's take another example of operational amplifier. And this application name is a differential amplifier. Differential, or let's say difference amplifier. So why we know that in the first module itself, we have called op-amp as a difference amplifier because we know that it has two input terminals and one output terminal named as inverting and non-inverting. And we know that it basically amplifies the difference between the two terminals. So VO equals to VID times A, where A is the gain. So in the open loop, when there is no feedback, this gain is very large actually. Ideally, it's infinite, and practically it's very large. So to employ such amplifier without any feedback is not practical because it may saturate the waveform output signal, and therefore usually we employ this amplifier in a feedback way, and that's why we use it as a difference amplifier. So how to use that? We study this combination. Let's say we have two input terminals, and the arrangement of the feedback resistances is like this, where R2 is feedback resistance and R1 is the first input, that is VI1, and another input VI2 would be connected in such a fashion like this. Let's call it resistor R3, let's call it resistor R4. And the gain obviously is indicated by that. So we know that to analyze this configuration, these are the two nodes where we have the voltages indicated by V1 and V2, and we know that the difference between these two, that is indicated by VID. So VID is nothing but V1 minus V2. That's the difference. So it has a name difference amplifier or differential amplifier because it is going to amplify a difference between the two nodes, the node voltages that appears at these two nodes, that is V1 and V2, and nothing else. It should be able to reject any other signals to amplify. It should reject to amplify any other signal other than the difference between these two input terminals. So having said that, we know that other properties of the operational amplifier. So let's indicate them by this way. These are the two currents that they are trying to enter. We call it as an input I positive and I negative because they are trying to enter through the negative and a positive terminals of the op-amp respectively. So we know that they are 0. IN equals to IP, that is equal to 0. Okay, and this is again due to the ideal characteristics, and because of this property we still say that this difference amplifier has a differential infinite resistance. The differential input resistance, that is the resistance between these two terminals, is infinity. Okay, and once we have these expression, how to obtain the expression for the output? So we can use the superposition. So in which we make sure that one voltage source is activated and while other is made 0, and we obtain the expression for output. And the next step, we activate the second voltage source and make the first one to be 0, and we again get the output expression, and then we sum both of these outputs to get the final output. So let's continue. Let us say VO1, we have to obtain this. So VO1, with this, the circuit combination would be like this. Let's say we have VI1 is activated. And this is R2 and R1. Whereas we do this arrangement where we have actually short circuited or removed the voltage source. So therefore, this V2, Vi2 is 0. And this is how we have this combination. So once we have this arrangement, we know that this is the node voltage V2, this is the node voltage at V1. So we can see that what is the gain that we can get here. Okay. So obviously there is no current flowing through R3 and R4 and the node voltage, because there is no source here. Okay. And at V1, we can write the expression like this. That is VO1 would be simply, it's a inverting amplifier. So minus R2 over R1 times Vi1. Okay. Because we know that there is this current trying to enter is 0, but since there is no current in this loop right here, that is I is 0, and we have only this current that flows. So this is the standard inverting amplifier that we've seen before. And once that happens, we can go back to analyze the circuit again, where this time we deactivate the voltage source Vi1 and again reactivate the voltage source Vi2. Okay. So we have this, and we again come back to the general theory. We have the gain to be A, and what we see here, we know that it is a case of non-inverting amplifier, because the this terminal is grounded. Another one of the terminal of resistor R1 is grounded, and this with this configuration we have this non-inverting amplifier. So VO2 would be written as V2 times, because that's the voltage appear at the positive input terminal. Now first we have to determine what is the voltage at V2. Okay, so let's take a look at this. We see that V2 would be R4 times Vi2 divided by R4 plus R3, simply a voltage division rule. Okay, and once that is obtained, we can get the expression as V2 times 1 plus R2 over R1. So this is the case of inverting and non-inverting amplifier. Okay, and once we have this, we can write the expression, that is VO2 is R4 times Vi2, R4 plus R3, 1 plus R2 over R1. So this is how we get the expression. So we know that VO1 is this and VO2 is this. So we can simply sum these two expressions together. So VO would be VO1 plus VO2, and we can just write these values here that we obtained here. So let's say equation 1, this is equation 2. So what is to be understood from these two is that we can get the final gain expression. Let's calculate it. This is minus R2 over R1 Vi1 plus, this is the expression, 1 plus R2 over R1 times That is your final output. And we know that VO is nothing but what we want is the difference multiplied by the gain, that is VI1 minus VI2. Okay, that's how we can have this expression. We can try to write it like this. Let's say R1 plus R2 divided by R1, and we R2 into VI2, R2 plus R1 minus R2 over R1, VI1, because we see that we have some assumption R4 equal to R2, and R3 is R1. Plug in these values. So we can get this expression like this. So we see that this factor goes away, and they are simplified like this. VI2 minus R2 by R1, VI1, and that further simplifies to R2 by R1, VI2 minus VI1. Okay, so this is your final output. So the gain is this factor. If we have this assumption, we make these registers R4 equals R2 and R3 equals R1. So that's your gain for the difference amplifier. So let's denote it as AD, differential gain. Okay, so that's how we get this circuitry over here, and this is how we can get the expression for the differential amplifier. Okay, so we see that final output VO is A times VID, which is R2 over R1, and note the sign, it has a positive sign. Okay, this is VI2 minus VI1. And that is your output. Okay. So that's all for this module.